So today I'm going to talk about some joint work with Luc. It's sort of a lot of work. We started out very small and we built up, and this is sort of the latest thing we've done, but it's, yeah. So there's a lot of things behind this, but I'm going to try to just give some basic ideas, just describe some of the things we've done, some of the technicalities. Try not to be too technical, but it is very technical work. So, okay, so the basic question is, though, not very hard to state, especially in this audience. So we have a domain in the plane, in the upper half plane, and so there's the unit circle, or at least half of it. And there's a strip of width t, and that's our domain, omega t. And the question is, do there exist any eigenvalues, L2 eigenvalues for this? So particularly, does there exist an L2 function? Now it has this funny measure, dx dy divided by y squared, and that's coming from the fact that we're looking at the hyperbolic metric on the upper half plane. So this is not the Euclidean metric anymore. And it also has this funny Laplace operator with the y squared out in front, which is because it's the hyperbolic metric on the upper half plane. And we're looking for Neumann conditions all around. It's actually known that it's not so hard to see that if you have Dirichlet conditions, there are lots of L2 eigenvalues, and they account for sort of a Weil's law's worth of eigenvalues. And so, but the Neumann, it seems like it's very rare to have a solution to this problem. So in fact, we'll show that there basically are no solutions for the generic t. So one thing to note about this measure, dx dy over y squared, distances get very small up in the so-called cusp as you go to infinity. And in particular, this has a finite measure. So it's not completely nasty, but it still has some non-compacity. So the answer to this question, Selberg, as you know, proved yes in certain cases. In particular, the case of 1/2. If t is 1/2, that's the famous modular domain, or at least half of the modular domain. And in that case, via the trace formula, he's able to prove that there are lots of discrete spectrum, Neumann discrete spectrum. In fact, Sarnak says that the reason he developed his trace formula was to actually see if there was discrete spectrum there. So for 1/2, and then for somewhat related reasons, it also works if this width of the domain is 1 over square root of 2 or square root of 3 over 2. Of course, they look like funny numbers, but they're just these numbers, right? And that pi over 3, pi over 4, pi over 6, those are just the angles of, in the right corner, that's just the angle of that side. So, so if you have that angle down there, so I guess I can use this. This angle is pi over 3, pi over 4, or pi over 6. The answer is yes. And in fact, not only yes, but there are lots. There's countably many. But then Phillips and Sarnak conjectured no. There's a paper that appears in, I think it's Journal d'Analyse, where they conjecture that if you're outside these cases, when n is an integer, and n is bigger than or equal to 3, then except for 3, 4, and 6, there are no L2 eigenvalues. So there's, now we know there's continuous spectrum here, so you say, where's the spectrum gone? It's all gone to the continuous spectrum corresponding to the cusp, The question is, are there any embedded eigenvalues in that continuous spectrum? Okay, and so then recently, Luc and I proved the answer is no, but if you look at the t in the range between 0 and 1, there may be a countable number of exceptional t for which you can have L2 eigenvalues, but otherwise none. Neumann conditions. Now, of course, this doesn't really answer the conjecture of Phillips and Sarnak because the integers represent the countable collection of numbers, but it gives sort of some indication that it's a very unstable condition to have L2 eigenvalues in this particular setting. And so I want to describe some of the ingredients of the proof. You know, it is kind of technical, but you know, if you spend enough time with something, things start to look pretty. And so maybe I can convince you they are. So let me just say a little bit about the background. This conjecture actually sits within a bigger framework, and it may explain why some of the people are interested in it, like Selberg and Sarnak. So the current philosophy is that there's certain spectral dichotomy for hyperbolic surfaces involving arithmetic. So let me remind you, the hyperbolic plane is the upper half plane with this funny arc length element where you multiply by 1 over y, and the measure is, again, divide by y squared. Okay, so this is non-Euclidean geometry. This is the basic model for non-Euclidean geometry of the non-compact type. So the corresponding Laplacian, the thing that commutes with pullback by isometries, is this thing. And what we're interested in general, or at least a lot of people in pure mathematics are interested in, are isometry groups of these manifolds, of the upper half plane. In particular, we want to look at a cofinite discrete subgroup with cusps. So cusps are they're locally modeled on that strip that I indicated at the beginning. So they have finite area. Topologically, they're just points removed from a surface. So I want to get so when I act by my group gamma on this upper half plane, I'll get a surface with a hyperbolic metric with finitely many punctures, but it'll be complete, and the completeness tells me I have cusps. Okay, so that's, and then this operator, since it commutes with pullbacks, it descends to an operator on H mod gamma. If you'd like to think about, this is sort of the analog, the non-Euclidean analog of a torus, this H mod gamma. So you get sort of this periodic operator on the upper F plane, where gamma is the periods. And you get this funny spectral decomposition, which goes back to Selberg, which says that you have sort of some L2 eigenvalues in general, and you do have them in some cases, plus some other part which involves what are so-called Eisenstein series. There are some generalized eigenfunctions here that are responsible for the continuous spectrum. Okay, so the basic, the dichotomy is this, that it seems that if the group gamma is arithmetic, meaning that it has a lot of hidden symmetries, then the pure point spectrum, this part, has Weyl density 1, and if and only if. So by Weyl density, there is a Weyl's law here that was proven by Selberg. You can actually look at, you can interpret, you can take the resolvent and analytically continue it and count the number of poles of the resolvent in a certain ball, and you get a Weyl's law, but there's going to be some scattering poles coming from this part, and then there are going to be some L2 eigenvalues part. And when I say density 1, I mean who dominates in that Weyl count. And the conjecture is that this term dominates if and only if gamma is arithmetic. So arithmetic is very rare. Arithmetic means that you have, if you have your group and you can conjugate by elements of SL2R, if you intersect that conjugate with your original group and you have a finite index intersection, and you look at that set of elements in SL2R that does that. If that's infinite, then you're arithmetic, and if it's not, you're not arithmetic. And so SL2Z is an example of an arithmetic group. There are only finitely many in each moduli space, in the sense of what Richard talked about. Okay, so you get very special. These only happen, you only get pure point spectrum if and only if something very special and beautiful happens. If and only if a number theorist would be interested. Yeah, okay. Okay, so now I want to return to our problem. That was the background. Question? So the thing we're going to try to exploit here is, and this is not new, goes back to Selberg, is to exploit the Fourier decomposition in the cusp. So here I have a cusp, but I'm going off to infinity, and what I'm going to do is fix a y and do the Fourier series of my function in x. Okay, so I'm basically going to do separation of variables. It's been a it can be used great effect in this problem. It's not really separation of variables because of course we have this part down here, but that'll have to be taken care of by the coefficients in the Fourier decomposition, which we really don't understand, but we'll do the best we can with it. Okay, so here's the Fourier decomposition, and because I'm talking about Neumann functions, I can just talk about cosines. And it depends on the width, of course, of my domain T. Now, if I take these guys, this guy, and I suppose it's an eigenfunction, then the individual Fourier coefficients by separation of variables essentially are going to have to satisfy this ODE. So basically, all I need to do is solve this ODE and put take the right set of solutions and then sum up, and I get a solution. I get my U. Of course, it's easier said than done. I need to understand these guys pretty well to do that. So I want to point out a couple things. So this is actually gives rise to a classical special function called McDonald-Bessel functions or modified Bessel functions. So they're well understood, the solutions to this. But one feature is that y here is positive, in fact bigger than 1 in my case, or sorry, bigger than a half, I guess, but we only care about y bigger than 1. It only has at most 1 0, and so this equation has a turning point. And that turning point will be very important to us. We'll be able to use the Airy functions. So a lot of our analysis comes down to understanding Airy functions. Okay, so let's look at the solutions to this ODE. So let's look at what happens when L is 0. So L is 0, you can ignore this, and then you can explicitly solve and see that U0 looks like y to the 1/2 plus something oscillatory. Okay? And here E, the energy is, the eigenvalue is 1/4 plus R squared. So this is known to Selberg. I mean, this is what he used. Yeah. Okay, so notice that, well, we'll see in a second. Let me see. So if L is bigger than 0, then we actually do, so this is, if L is 0, this is oscillatory. If L is bigger than 0, then you actually get a turning point, and the behavior depends on the location of y with respect to the turning point. So if we look at, for y big, this term will dominate, which is positive, and I'll get exponential either growth or decay in y. Okay, so basically we're going to throw away the, certainly the exponential growth guys are not going to be in L2, so we're going to throw those away. Okay. So really when we're interested in L2 eigenfunctions and we look at the expansion, we need to know that UL is sub-exponential, meaning that in particular UL is like minus L pi over t, so it's going to decay very rapidly. Also we need to know that U0 is equal to 0 because y to the 1/2, even though we're dividing by y squared, y to the 1/2, when I square it, I get y divided by y squared is 1 over y, which is not integrable as y goes to infinity. So we need to have U0 is identically 0 in order to be sure we're in L2. So this part has to be 0. So these things are called Cusp forms. An L2 eigenfunction is called a Cusp form, basically because its zeroth Fourier coefficient is 0 in the cusp, in each cusp.
So what is R again?
Yeah, R is the square root of the eigenvalue minus a quarter. So it's basically the square root of the eigenvalue. Yeah, so it's, here it is, yeah. Okay, now, okay, so now we've moved past Selberg and into Lax, Phillips, and Colin de Verdier. You know, they wanted to, in some ways they wanted to avoid continuous spectrum or be able to, or to work past it, work around it. And in order to do this, they have this nice construction originally due to Lax and Phillips of creating an operator which is like the Laplacian, which is compactly resolved and therefore has discrete spectrum. So the idea is that the problem we had was that the zeroth Fourier coefficient is 0. That means we're out of L2. So what we're going to do is truncate the zeroth Fourier coefficient past a certain point. So we fix a point B, bigger than 1, and then we require that all our functions be 0 past that point. And then we restrict to the Laplacian there, and then we do a Friedrich extension on that smaller domain, and we get a new operator. And that new operator is called the Friedrich extension. It depends on B, but B is going to be fixed for us once and for all. Okay, and again, so this operator actually is compact because we've gotten rid of the bad part, which is the zeroth Fourier coefficient. Moreover, as a function of t, you can apply Kato theory for t positive up till 1, and all the eigendata, the eigenfunctions, eigenvalues vary analytically with t. That's something we'll use quite strongly. The next thing is, if you have something which is an eigenfunction for the usual Laplacian, well, it has to have, since I'm talking about an L2 eigenfunction, then certainly its zeroth Fourier coefficient vanishes to begin with. And therefore, it turns out that it must be an eigenfunction of this operator. And conversely, if you know that you have an eigenfunction of the cutoff Laplacian, but you know that when you go below B, your zeroth Fourier coefficient is 0, then you're also a eigenfunction of the original Laplacian. So I can go back and forth as long as I know what the zeroth Fourier coefficient is below B. Yeah.
The penultimate one here, I don't understand this.
Which one?
The grad squared u equals EU implies the cutoff one.
Why does it apply the cutoff one is? Because this is a smaller domain. All I did, so I restricted, so if it solves the equation here, well, I see what you're saying.
Yeah.
Well, sorry.
So do you mean if u vanishes above B? And
well, right. If this is true and I have an L2 eigenfunction, then automatically from what I did before, the zeroth Fourier coefficient has to vanish for all y. And so therefore, then it belongs to the domain. Sorry. No problem, no problem. Okay. Now, one thing that we use and it's also been used a lot before us, is that if you have eigenfunctions ut, a family of eigenfunctions, depending analytically on the parameter t, then the zeroth Fourier coefficient is also an analytic function. And so, yeah, that's where we get the genericity result. Okay, any other questions about this? So this is a nice technical object that helps us deal with the continuous spectrum, or at least avoid it. Right, so what we're going to do to prove that we don't have solutions generically is just show there don't exist any eigenvalue branches with ut0 is equal to 0. The point is that an analytic function, its zero set can only be countable. And so if I look over all, so if I knew this, then there's no way I could have a lot of t's where I had L2 eigenvalues. Okay, so that's just a, Okay, so all those ideas were actually done, there's lots of work on this problem done by people like Colin de Verdier, Lax and Phillips, Phillips and Sarnak, well not Lax and Phillips, Phillips and Sarnak, Wolpert, Vinkoff and Balsev. I'm sorry, I'm not, since I'm being recorded, it's kind of dangerous, but I don't think anyone in here has actually worked on this problem except for Luc. But there, so I want to say what our new ideas are, what we've done. So we've taken this model problem, and we have again this omega t, this width t, and what we're going to do is study eigenvalues as t goes to 0. In my thesis about, well, I don't want to say how long ago, I studied where t is going to a point where you get this line. So that was my thesis. And it's not a very singular perturbation, so on the other hand, it's not as useful as the one we're about to see. So we're going the other way now. I'm going t goes to 0, so with Luc and I. Okay, so we're going to do a proof by contradiction. Luc is the master of proofs by contradiction, if you need one. So each eigenvalue et, we're going to show that each eigenvalue et tends to 0 for the cutoff Laplacian, which is essentially the same, for our purposes, is the same as the usual Laplacian. But then we're going to show that if ut has zeroth Fourier coefficient, which vanishes for all t, just for some fixed y, for example, then et can't go to 0. Okay, and that'll give us a contradiction. So we'll show both, so they must be false. So they can't exist. The point is that now the UTs, which I'm assuming have this property, can't exist. Okay, so we have two methods. One we like to call asymptotic separation of variables. And that we didn't actually start it in a previous paper, but we've developed it further in this work. And now a newer idea is crossing avoidance. So we're going to actually use the fact, or well not fact, but we're going to use the idea that eigenvalue branches can't cross. It's actually crossing avoidance between the eigenvalue branches of two different operators, which I'll explain in a second. Okay, so that's the idea. So what I want to do is explain these two ideas, or start off by explaining sort of what I mean by asymptotic separation of variables. And it works in more general cases than what I'm doing here. In the previous paper, we showed that if you look at the generic triangle, Euclidean triangle, the spectrum is simple for Dirichlet or Neumann eigenvalues. So it doesn't work just in hyperbolic setting, it works in other places too. It works basically when you have a multidimensional problem where you can collapse geometrically to one dimension, where you can do separation of variables or collapse everything to an ODE. And that's what we're doing here. We're going to collapse this width to 0, and so in the limit we're going to basically have a line. But we're not actually going to collapse. Instead, we're going to keep the domain fixed and collapse the operator. So we're going to actually look at it slightly differently. So we're going to rescale first all the omega t's so that they have width 1. So we're going to get the right scaling. And it's just a horizontal rescaling. So the circle becomes now an ellipse. And so now the domain is less curved. And in particular, so we make these changes of variables, rescaling by t, and then that should be an x prime, my first typo, x prime, and then the volume form changes accordingly. Now notice, when I rescale, this domain is very close to being a rectangle, and that's what we're going to exploit. Essentially, we're going to exploit the difference between the Laplacian and this rectangle, for which we can do a separation of variables, and the Laplacian on the larger domain. And actually, what I should say here is, now that we've stretched, I should say omega t stretched is like 0, 1, 1, infinity. So this is before stretching. So this, now I've rescaled to have length 1. Okay, but the operator changes. So I'm going to be thinking of everything in terms of quadratic forms. And so I'm interested in Dirichlet form. So here's how the operator changes. And then right. And there was a y squared out in front of the Laplacian, but it gets canceled with the y squared in the measure. Okay, so I haven't forgotten the y squared, I just canceled it. And then again, here's the L2 inner product. Okay, so this is the operators I'm going to work with. And I'm going to think about them, operator I'm going to work with, but I'm going to think of it as in terms of quadratic forms. So I have a horizontally stretched domain, omega t. I'm approximating it with a rectangle of fixed width, 0, 1. And in order to compare the two, I'm going to use a diffeomorphism supported. By supported, I just mean that the differential differs from the identity only for y less than b. So I'm only going to be perturbing the domain for y less than b. And I'm going to map one to the other. And you can do this in a nice real analytic fashion. And there are many different ways to do it. Ultimately, it doesn't really depend on how you do it so much as you got to do it right. I mean, yeah. Anyway, so you pull back. I'm going to pull back my quadratic form on that omega t onto the rectangle, and that of course makes it no longer as nice to look at. But at least now I can look at its asymptotic expansion on a nice domain. So I'm going to expand, we're going to expand this quadratic form on Qt, and again, it looks like what would happen if I hadn't pulled back, except I have some error. The error, this is the error coming from doing the diffeomorphism, and you can show it's essentially O of 1. Now, it's not so nice, these t squared and these t's, so because I don't really care about the size of the eigenvalues, I only care if they exist, I'm just going to rescale my operator by multiplying by t. So I'm going to redefine Qt to be the pullback of t times that quadratic form. So this is just a rescaling to make things look nice. Oops, didn't want to do that. Now, so I've now instead of, yeah, so these things cancel, I multiply by t. This cancels with that, and I get this, and then I get an O of t error. And then this is sort of my model quadratic form, my model operator, which is essentially the same the one that is, comes with doing separation of variables, the McDonald-Bussell functions. I'm going to call this part AT, and then the rest, you can actually show that the remainder in this expansion is bounded by AT, in terms of AT. So this is going to be my model, what I'm going to look at to understand the eigenfunctions, because this can be, I can just invoke separation of variables in this part, and then I have to worry about the remainder. Okay, so now we come to the setting. So this gives us the setting that we call asymptotic at first order, which a lot of the things that we develop apply to. So we have two quadratic forms, AT and QT. Sort of QT is the one you want to understand, and AT is the nice model one that admits separation of variables. And what we know is that the difference between QT and AT is essentially bounded like this. So here I've written it in the polarizations of QT and AT. And moreover, you can actually check, I didn't do it, but you can check that if you take the derivative with respect to time of QT and the derivative of AT, then they're bounded by something involving AT. Okay, so this is what we'll call asymptotic at first order. So QT and AT are very close. And the idea is to transfer information about AT to understand things about QT. In this particular case, A dot is 2t times the integral of uy squared, because it only involved let's see, go back. It's only involves, here's the only involvement of t in AT. So when I take the derivative, I get 2t, and then this part goes away. So there's the derivative. In particular, it's positive, and in fact, it's less than or equal to 2 over t. So this is a nice feature in this particular case. So the logarithmic derivative is bounded below and above. In particular, what this says is that we already know that the eigenvalue branches of AT will converge as t goes to 0, because A dot is positive. Right, which I just said. Okay. So here I want to give just one example of what you can do with just these conditions, these abstract conditions, just as a toy proof of something. And it's the only thing I'll prove. It's very short. So suppose you have two quadratic forms, AT and QT. They're asymptotic of first order. And you know that A dot is positive. Then each real analytic eigenvalue branch of QT, so this is supposed to be an eigenvalue branch of QT, converges. So we just said that the AT eigenbranches converge, and now I claim the QTs do as well. So the proof is, look at your eigenvalue function branch, UT associated to ET, and then this is a basic formula that the derivative of the eigenvalue is essentially given by the quadratic form divided by the norm squared. And then since asymptotic at first order, we know that Q dot minus A dot is an absolute value less than C times A, but that means it's just bigger than minus C times A. Okay? And then I also know that A dot is positive, so I can get rid of that part, and I get just minus C AT UT. And then since UT is an eigenfunction, I can use this equation, substitute in here. I get that. Right? So I just substitute in. I learned how to use slash only yesterday. It's a very nice little command. And then we know that, oops, I don't know how to use this though. Then we know that since it's asymptotic at first order, we also know that that 2 times QT is bigger than AT, right? AT and QT are close. So 2 times QT is bigger than AT, which means this. And then QT of UT is the same as E times UT, because it's an eigenfunction, right? So the quadratic form, so QT of UT is just ET dot UT squared. And then you can cancel the UT squareds, and you divide both sides by ET, and you get this, right? And this shows that the negative variation of the log of ET is bounded, but we know that ET can't go below 0 because these are positive quadratic forms, and so this is enough to tell you that ET converges. Okay? So this is the kind of arguments that we use in just a sample of things we do with in this paper. Okay, now remember what we really want to show is that ET must go to 0. And ET does not go to 0. That's the contradiction. And so we have to investigate further. It requires a little more work to get, we have to do a lot more than this. This is just the beginning. We'll have to use very specific behavior about the eigenfunctions of AT. So we're going to use, in particular, quasimodes. And we're going to construct them from spectral projections. And so we want to take our UT and project it onto the spectrum of AT in certain energy windows. Right? So here I'm starting with an eigenfunction QT of u, v. So that's the weak eigenvalue problem. That's just saying u is an eigenfunction. And now I take an interval in energy dimension, and I want to project this u onto the AT eigenspaces where lambda is an I. So I look at lambda, here's an eigen, always for me, lambda is an eigenvalue for A, whereas E is an eigenvalue for Q, right? So these are eigenvalues in I. Okay, so so the proposition is this is a quasimode at energy at order T with energy E. So AT of that projection E times W, this is, well, it's what it is. It's a quasimode, okay? So again, we're doing this all weekly, so that's for all V. And then, moreover, using similar arguments, you can show that this happens, that AT of, this is using also the, always here I'm assuming that I have the asymptotic at first order business. This is very important. It all goes into this. So in particular, I get bounds on the difference between U and W, where, so W I almost assume is the same as U. But what's nice about, of course, about W is it's made up of eigenfunctions of A. And A can be understood by separation of variables. Okay, so here's one consequence for real eigenbranches of QT. So we're going to take T goes to UT, an eigenfunction branch with eigenvalue branch ET. And we're going to look, we're going to fix an interval I. I is going to be fixed. And we're going to project onto the AT eigenmodes. So here's the proposition. This is actually something that holds just for asymptotic with, so our, you know, in the general case of our asymptotic at first order, as long as A dot is positive, okay, or non-negative. So this function ends up being integrable over 0 T naught. And for similar reasons, similar arguments give that actually A dot minus E dot times UT squared is bounded in terms of UT. Actually, I think this is supposed to be UT squared. In fact, it has to be UT squared. Okay? Okay, so this is going to actually come back and I'll explain. But this is the type of theorem you can prove using this asymptotic at first order. So it's integrable as a function of t. So if I integrate over small t, it's nice. It doesn't blow up. Okay, so so that was actually, most of that was all very general. Now we have to use some pretty specific information about what A looks like. So A, remember A, this is the definition of A. And now I'm just going to subtract off E times the the norm squared of u, but remember the norm squared of u involves this y squared. So if this is the same as that. And now I'm going to bring this term over to the other side, and then I hope I did my algebra correctly. It was like 11:30 last night. But so anyway, I think this is okay. Did I get missing an integral on the right? Oh, is there an integral here? Yeah, there is actually an integral here. Sorry, thank you very much. There's an integral sign there missing. Very good. So, but in any case, if you remember the integral here, if I take the integral of t squared uy squared, that was essentially the same as a dot. Remember a dot was 2t times uy squared integral. So if I divide both sides, if I multiply both sides by 2 over t, then I get the right thing for a dot here. This becomes a dot, and then this stuff becomes this, and this stuff becomes that. Okay, now this is a nice formula because this is basically the quasi-mode stuff. So if I have a quasi-mode, then I can make this small. So if I have so that's good. See, what I want to do here, I guess I should keep you in mind, is I want to show that E is going to 0. So how do I show E is going to 0? Well, one way to do it is show E dot is very large. So I have this function, and I want to show it goes to 0. So I want to show the derivative is very large. So I want to show, well, Q dot and A dot are essentially the same. And basically, Q dot of u is E dot. So I want to show that this is very large. That's how I'm going to show things are going to 0. And they look good because there's this t factor here. So it looks like it should be 2 over t here. But this could have a problem with the sign, but it doesn't matter because this will be small for the quasi-mode reason. And then I have this stuff which will be reasonable well, we'll get to this in a second, if I can make sense here, of this part. So it's going to come down to understanding this part. Okay. Okay, so now, in order to understand that part, I want to use separation of variables. In particular, I want to expand this in cosines, expand this part. So, again, u is this, that's my cosine expansion just like before, except now I've normalized, get rid of t, because I've set the width to be 1, and then I have this, and then the AT thing can be split up. So if I write u as a sum of ULs, I'm sort of being a little bit sloppy here, but expand u and I write so this is going to be a sum of the AT of ULs, where this is AT. Okay. And in particular, the spectrum, it separates, right? So the spectrum of AT is basically the spectra of all these different operators. And so this is now a ODE operator. It's a quadratic form associated to ODE, and I understand it through Bessel functions. And you can actually check that the eigenvalues for t small look like this. They look like pi L squared plus c times t to the 2/3 O of t. For L larger than 0. For L equals 0, they look like quadratic in T. Okay, so here's what they look like. These are the eigenbranches of AT. So again, for each integer k, L, or whatever it is, you get all these eigenbranches. If you rescale by 2/3, they look linear coming in like that. And then there's the ones that are going to 0. Okay, now A dot is nice with respect to AT, so A dot is actually the sum of the A dot TLs. And so, and each A dot TL it has the same picture, except that now instead of having a U x squared, I have pi L squared times V squared. So this is what I wanted to do, was to now look at this as an ODE operator. And again, this part is going to be small. And what I want to understand is, can this be small? I don't want it to be small because I want the eigenvalues to be driven down. And so there's a non-concentration result. It's basically understanding area functions, or I think there's a way of understanding it semi-classically, but you have to ask Luc about that. He has probably the right point of view. I only understand it from kind of 19th century mathematics. But you can show that this, this integral is large, meaning at the turning point, so this is what's happening at the turning point. You're getting a 0, but it's saying that even though this is 0, your norm is still big. So your norm must, so W squared must be big away from the turning point as well. Okay, but that's good because that tells us that this is relatively big, this is small, and so A dot has to be big, which means the eigenvalue is going to have to drive down. Okay, so how many minutes do I have? How many, are we supposed to do 50 or an hour? 50.
About 5 minutes.
Okay. Okay, 5 minutes, okay. Yeah, so anyway, so using that, so using that fact, the non-concentration fact, and also this expansion for A dot, what you can do is show that no eigenbranch can go down to, we know each ET goes to something, we already showed that. But what you can do is show it doesn't go here, it doesn't go anywhere in between. It has to go to some pi L squared. And the proof comes from actually another proof by contradiction. We compare the fact that we know it must be big if you have a quasi-mode versus the integrability condition, which is, I don't know if that's going to click it or not. Oh, I don't know how to click that. There's some, remember there was this condition back here. So contradicting with this, now I don't know how to go back. I have to slide through it, I guess. Yeah, so anyway, so using those, you can show that this kind of situation actually can't happen. And in fact, the only thing that can happen is ET has to actually end up converging to a pi squared t. Just like the ATs. So all the time we're trying to promote all behavior of AT eigenvalues into QT eigenvalues. And in this case, that works. Okay, and then, yeah. So we know it goes to some k pi squared. We really want to show it goes to 0 pi squared. We want to go to 0. And to do that, we have to work a little harder. So again, here WT is going to be our spectral projection. But WTL is we're going to only project onto eigenspaces that go to some pi L squared. Now we do know, and here we're taking the projection so that we're taking the interval I to contain the limit of the eigenvalue branch. So ET is converging to something, and I'm taking my interval in which I'm projecting here. So I know that there are some pi k modes that actually converge. So k is the place I'm going to, L is the general integer, k is a very specific one. It's the one where E is tending to, pi k squared. Oops. And if you can show that that kth mode relative to the entire quasi-mode is small, this is just part of this, right? If that's small, then you can show that E dot is like 1 over t, which is driving it down very fast. Of course, this doesn't necessarily always happen, but we can make it happen by noticing the following. So here's the crossings part of the crossing avoidance issue. So it turns out if your ET is close to some eigenvalue branch of AT which is going to 0, AT0 is the guys who, in AT guys who are all going to 0. If you cross, so that in particular, if you cross at in this window of t to the 5/3, then you can ensure that the WTK mode is small relative to WT. And this is actually probably the most technical part because it requires us to do some really fine area approximations. And we actually have to look at so here BT is the difference between QT and AT at first order. So there's an expansion. QT is equal to AT plus TBT plus O of t squared. So BT is the next order in the expansion. And you can write it out. It looks like this, where P is some function which depended on how you did your diffeomorphism to begin with, comparing the domains omega t and the rectangle. But you have to show that this thing, this sort of off-diagonal term, is large enough. And then you can prove that if you have crossing. So this is the eigenmode for the AT0, and this is your mode. And basically, there's sort of an interaction between those two. That's what this represents. And you need to show that interaction is large enough, and then you can guarantee this condition, which tells you that your derivative is very large. Okay, am I done? Okay, so that's the 0th order approximation of the proof. Again, we're going to assume that there exists a UT with that's a Cusp form. And on the one hand, I didn't discuss this, but we know E0 has to be bigger than 0. Basically, the idea is that just like with the AT branches, there's no way you could have a 0th mode in your, unless you were, I haven't discussed this, I don't have time. If E0 is bigger than 0, then you get infinitely many eigenbranches crossing ET, because these are all going to 0. The eigenbranches of AT0 are going to 0, and so you'll have infinitely many. And then the previous two lemmas imply that each crossing you're going to get a lot of change in the eigenvalue, and then if you sum carefully, then you can show that the resulting decrease to 0 will be fast enough to go all the way to 0. Okay? So that's it. Okay.
Is there any questions? Sorry, you have to use this mic.
You have to use the microphone.
Okay, so this is probably I just missed something somewhere, but it wasn't clear to me why this isn't proving. So this is depending on analyticity, isn't it? So why is this not proving that? Your result is that there's no eigenvalues for almost every t in 0, 1, but why is this not proving it for
all t? Yeah, I mean, it could be, and it does happen. Remember at the very beginning, for pi over 3, pi over 4, and pi over 6, yes, we do know there have lots of them. So what happens is, what we'll have is eigenbranches of QT, where at those particular t's, this is 0.
Okay.
So as a function of t, that ut0, so here's t from 0 to 1, and here's u0t. So this is and we can fix a particular value y, say. Okay, so this is the 0th Fourier coefficient. And then when we look at, say, 1/2, it crosses. And so there's what Selberg found was the fact you got one that had where UZ was 0, but generically it doesn't. So we don't know exactly. We actually can't tell you a particular t whatsoever for which there is no L2 eigenvalue. If you ask me which t's, I have no idea. All I know is that this function can't vanish except at I know it can't be identically 0. That's all we're proving. We found a contradiction identically 0. But we don't know where it's not 0. We have no idea. I mean, we know it's 0 at 1/2. We know it's 0 at the other places.
Is there any other questions? Actually, I have a question. So, so you did this diffeomorphism to the rectangle,
right?
And there was this when you expanded Qt in terms of AT, you had this error term,
right?
And I couldn't quite
see where it was.
How did you?
Well, it actually shows up here, and so this is the only place we really need it. It shows up. So here's the next term, basically. So Qt is equal to AT plus BT. Then there's even higher order, and this doesn't matter. We just need to have control on that. But here's the next order term. It looks like, and you can write out the entire expansion. And this P depends on that diffeomorphism here. Okay. But what's really important for this is that this P, which happens, the way we chose it, happens to be a polynomial for y between 1 and beta. It's important that this is non-zero. Otherwise, this would be 0, in which case, well, it wouldn't be 0, but this wouldn't work because there is concentration near y equals 1. So it comes up in here. You could use a different diffeomorphism and you get a different P, but you'll end up with the same result.
So that correction didn't affect this previous lemma, like the lemma of knowing that you converge. That was only to first order. That's all you needed to prove that.
To know that you converge, the ET converges, yeah. Now to get this, we didn't need that. We didn't need that. No. The only place we needed this knowledge of this term was when we needed to look at the crossings, make sure that crossings. In some sense, this should be thought of as the eigenvalues of A are pulling down the eigenvalues of Q.
Any other questions? Let us thank the speaker one more time.